So our speaker today is Jorg Wrachtrup, coming from the University of Stuttgart. Jorg got his PhD from the Free University in Berlin, working with spins and with someone who was interested in quantum effects, even though never lived to see the success of those things. And then he went on to the Technical University of Chemnitz, where he started pioneering the ability to measure and probe individual spins in a solid. And when he moved to the University of Stuttgart, he basically started realizing that these spins in diamond, in particular, that's something we'll be talking a bit about, were possibly a very interesting candidate for quantum information, and essentially spawned an entire field. And look forward to. Oh, and I should mention, he recently won the Leibniz Prize, which is, I think, quite a nice award from the German Physical Society. So congratulations on that. And we'll look forward to hearing what you have to tell us.
Okay. Thank you, Nate, for kind words of introduction, and also thank you for inviting me here. It's really a pleasure to be here, especially since we also try to run a joint quantum institute with a close by university, University of Ulm, and the distance we were talking about this morning is a bit larger than you have it here. It's probably about 60 miles or so. And we also try to run common seminars. You're trying to do it here. I wish all of our seminars would be that well attended. But we're working on it, and I got a couple of ideas on how to.
Do you offer free lunch?
Don't offer free lunch. No, we don't do that, and that's one of the things I take home with me. Okay, so once again, thank you for being here. What I would like to do the next 45 to 50 minutes or so is giving you an idea of what we are currently doing when working with spin systems, and in particular I would like to, well, there is a misprint here, I would like to tell you how we try to integrate those spin systems we are interested in, which today will be exclusively diamond spin systems, into devices and larger arrays and things alike. Once in a while I use the first transparency here to actually, first of all, tell you what kind of systems we are working with. First of all, this is diamond in most cases, and it's doped diamond. This is a doped diamond also. It's a blue diamond, as you can see, and it's blue because there are boron impurities into diamond, which is made out of carbon, as you know. And this boron is a color center, and it's also, by the way, makes diamond a whole semiconductor, and it's these kind of color centers we work with. And there is another reason why I show this transparency, because it has something to do with science funding. Actually, this diamond here is a particularly well-known diamond. It's called blue Wittelsbacher, and Wittelsbacher, that's a local royal family. I'm working in southern Germany, and there were royals there governing that part of Germany for centuries, and one of those were the Wittelsbacher, and they actually were in the possession of that stone, and they needed to sell that stone 1927 or so, during the first world financial crisis. They needed some money, and they sold out one of the most precious things they can sell, and this was this diamond. It went to an unknown buyer, and it came back to the market a couple of years ago, 2008, second world financial crisis. That unknown buyer needed some money, and it was the state of Bavaria, this is where the Wittelsbacher were living, considering buying back that diamond. And they set aside a sum of something like 20 million euros to do that. That was auctioned in Sotheby's and in London. And so they had this money, and they didn't make it in buying the diamond. It went to, once again, an unknown buyer, most probably in the Arabian world, for 25 million euros or so. But that money was there, and once in a while there are wise decisions being made in politics, and the decision was that since the money is there, let's spend it on something which is useful, and useful is, at least that was the reasoning, is science, and part of the money, guess, right, ended up in our lab. So that's why I'm able to tell you a couple of stories.
But you don't have that diamond.
No, the diamond actually went to some unknown buyer. I have no idea
And this is a wholly natural diamond, presumably shaped a bit smaller.
Well, this hole in there is just to tell you that what we are doing is actually having a deeper look into the diamond and see individual of those defects, or even try to, write these regular arrays of defect inside the diamond. So that's, by the way, this young lady here, that's the princess with whom this diamond came to Bavaria. It was the bride's gift of a Spanish princess together with the woman, this diamond came to Bavaria. Telling you that there were times in Europe when money flow was from south to north and not the other way around. Okay. It was not only money, it was also beauty.
We won't quote you.
Come on, let's concentrate on science. We can discuss about politics. Okay, so just to give you an idea of the activities we're doing, and also give you an idea of what I'm not going to talk about. So today I'm mostly concentrated on making these spin arrays, interacting spin systems, and also using them for quantum sensing, as you see here in these first two boxes. We also, if it comes to quantum, we also work a bit on quantum plasmonics. That is, we are really interested in trying to understand what kind of quantum properties plasmons do have. Is there Photon interference and these type of things? And if they qualify for large non-linearities, potentially on a single plasmon or photon level. So that's an activity which is also related to diamond, but which I'm not going to talk about today. Rather, I'll start, with how to engineer spin arrays into diamond and where they are. So once again, these diamond defects, I guess most, or at least some of you have heard about them, are nothing but impurities inside a carbon lattice, and the one most people work with, and so do we, is a nitrogen impurity inside the diamond lattice with the next nearest neighbor vacancy. Diamond has a band gap of around 5 electron volts, so it's a decent and a very good insulator. It's optically transparent, obviously. And this defect here is a molecular structure inside the band gap of diamond. So it's easily optically accessible. Ground and excited state are split by roughly 2 electron volts, which is very convenient for experiments. And it has a very strong fluorescence, not as strong as quantum dots, but as good as a molecule. So it's very easy to see single of those defects inside the material. Diamond is, as a solid state material, is characterized by a very high Debye temperature, basically telling you that there are hardly any optical phonons being excited at room temperature. Right? So this is much lower than room temperature, no optical phonons. And this is one reason why spin orbit coupling and spin relaxation in general, due to phonons in this material, is very low. And that is a big exception. I only know one other material in nature where this is the case, and this is silicon carbide. All other solid state materials usually have very fast spin phonon relaxation, and a good material to exemplify that on is gallium arsenide, which has a spin relaxation times on the order of sub-millisecond at 2 Kelvin. And at room temperature, this goes into the nanosecond or even sub-nanosecond region, whereas in diamond, we have room temperature spin relaxations of 10 milliseconds. And that makes this system in a certain sense outstanding. Also, it's diamagnetic, so if you have spins inside the lattice, that is, or you have very few spins inside the lattice, that's a moral of the story. Now, this defect is paramagnetic. It's a spin triplet ground state. So the ground state is splitted into 3 sublevels, m sub s0 and plus minus 1. And the photophysics, the built-in photophysics of that system, once again, it's a molecular system, so it's a relatively low symmetry system. And it's the photophysics of that molecular system of this specific symmetry actually resulting in the fact that there is strong optical absorption from this m sub s0 ground state, and there is strong fluorescence to that state, whereas the other states are much darker. So you can drive magnetic dipole transitions here. And you can just look at that fluorescence as a function of the frequency of the microwaves you shine in here. And you see when you are in resonance, you pump the system from that bright to the dark level. And that is indicated here by the drop in fluorescence intensity. And because we have low spin-orbit coupling and we have no strong coupling to other magnetic degrees of freedom in the system, you can also, for example, coherently drive those that spin here. And that is shown here just by looking at the fluorescence intensity as a function of the duration of the microwave pulse you pump here. And what you see here is nothing but Rabi oscillations. And the typical relaxation times for these experiments are on the order of milliseconds, whereas typically the Rabi oscillations you can drive with frequencies of gigahertz. So you have a high fidelity, single spin operation in that system, and that is actually what caused lots of the excitement and lots of the activities in this field. Now, a single electron spin may be nice, but of course you would like to, you would like to do more than just a single spin. And there is one natural resource in that system, which only now people, it was clear from the beginning that it's there, but only now people really try to make use of it and exploit all of its aspects. And these are Nucleus Banks. So this is a symbolic representation of the diamond crystal. Here we have the electron spin, the two unpaired electron spins, which are, this is a point-like wave function, so they're mostly localized at the site of the defect. But although diamond is made out of carbon, and carbon is 99% carbon-12, that is, there is no nucleus spin associated with carbon. 1% of all the carbon nuclei in the surrounding are carbon-13, so they are spin 1/2 systems. And so every 100th lattice site basically is a nucleus spin, and the electron spin couples to those nucleus spins. And the coupling is in part contact, so only the very first carbon-13s here have strong contact hyperfine interactions. The rest is dipolar coupling. So this hyperfine coupling then depends on distance and on orientation. And I've shown you here 3 examples. The first example is coupling of the single electron spin to one carbon-13 spin here. And you see, instead of just a single resonance line, meaning a single two-level system, you have 2 resonance lines saying that you have 2 two-level systems, and so on and so forth. You can add another carbon-13 here, and then you have you increase your Hilbert space. Once again, you can add a carbon-13 here, and you increase Hilbert space once again. And of course, you understand in very great detail on actually what the structure of the Hilbert space is like, and what its dynamic is like, because you have a finite set of nuclei and interactions which are very well defined. So typically we describe now the dynamics of these systems here by methods like cluster expansion, which in principle, in multi-particle systems, you do a decent understanding of what's going on there. So
now, those are real data from real diamonds?
Oh yes.
So you're going to tell us how you pick on a particular
that's a good remark. Thank you. Of course, what I'm showing you here is, you look through. There's no way to place your carbon. At least we have found no real good way to place carbon-13s. So what you do is you just scan through your crystal, look from one defect to the other, and just by chance find one where there's one carbon-13 in the first shell, which is like, you need to scan through 30 to find one here in the first shell, and then to find 2, and so on and so forth. So probability goes down. This is, by the way, taken by carbon enrichment in diamonds. So you take crystals which have more than 1%, like 10%, 20%. To make you find one of these electrons coupled to 3 carbon-13s within the lifetime of your PhD thesis. Well, anyway, I think you don't need to rely on that extensive searches, because you definitely know there are the carbon-13s, you don't know where they are. And you just need to devise good enough methods to find carbon-13s even if they are very far apart. And we did that recently, and I'm not going to tell you how we do it, but just to give you an idea, what we can do right now is we can sense carbon-13s which are 3 nanometers away, which is on the order of 10 lattice constances, right? And just to make a comparison here, we were looking at interactions which are on the order of, say, 100 megahertz. And here now we look on interactions which are on the order of 100 Hertz. Right? But because you have a dilute gas of current 13s, you can do that, right? You just characterize your spin cluster around, and on average, you find 4 to 5 current 13s which throw strong coupling to the electron spin. And that's an extremely useful resource, especially because coherence and relaxation times of these nuclei, in particular when they're a bit further apart from the electron spin, are really long. So T1 at room temperature are hours, and T2 is on the order of seconds, as it has been recently shown. So once again, this is per se, this is a badly defined quantum register. You need to characterize each and every electron spin node. But once you have done this, you can work with these carbon 13s. So one consequence of having these long relaxation times is that, or one characteristic of these weakly coupled nuclei are these long relaxation times. So basically they are very much decoupled from the electron spin dynamics. And this one can use to really measure the quantum trajectory of those current 13 nuclear spins. And I'll just give you an idea of how we do this, and then I'll conclude on this part of the talk already. So imagine, we have a nitrogen 14 spin. I mean, this is a nitrogen vacancy center, so there is always one nuclear spin, the nitrogen 14, which is present. Now, the nitrogen 14 is a nuclear spin 1 system. So each electron spin level, say quantum state 0, is split into 3 nuclear spin levels, 0, -1, and +1. That is the case for this one, and that's the case for the, say, -1 electron spin sublevel also. What one can do is, in order to read out a specific nuclear spin state, is doing a pi pulse or a C0 gate on this electron spin transition. And if you prefer frequency space, so every electron spin resonance line here is split into 3 hyperfine components, and we just now do a selected pi pulse on one of the hyperfine components, just addressing the nuclear spin when it's in the, say, -1 manifold. So we do a C0 gate conditioned on the nuclear spin state -1. And if you do that, then, and if you plot the fluorescence intensity as a function of time, you see as soon as you apply the C0 gate that there is increased fluctuations, and if you plot that on an extended time scale, you see that you have in total 2 signal levels. One where the nuclear spin is in -1, and the other one when it's in one of the 2 other states. So this is nothing but looking at the quantum jumps of the nitrogen nucleus between 2 of the 3 states. And that is a room temperature experiment, and that is possible because even though the nitrogen is very close to the electron spin, because of the relatively weak hyperfine coupling, it's decoupled from its dynamics. Once again, the T1 of the electron spin was a millisecond, right? And now we talk here about time scales of seconds, and the average duration of that bright level here is nothing but the T1 of the nuclear spin. So T1 of the nuclear spin is seconds as compared to milliseconds for the electron spin. And this is why you can do that. Now, of course, you have these 2 intensity levels, and you can define a threshold that gives you a value for the fidelity for separating these 2 spin sublevels. Now, nevertheless, one sees these dynamics, and you can ask yourself, why is the nuclear spin, jumping around at all? And one of the reasons, of course, is that eventually there is spin lattice relaxation. There will always be a finite number of phonons, although this is very small in that system. But another reason is that not all terms in the Hamiltonian, which describe the interaction between the electron and the nuclear spin, commute. So this is not a perfect quantum non-demolition measurement. That's basically what I'm saying. And that's the Hamiltonian describing the system. Now imagine we would align our magnetic field along, say, this direction, which we call the z direction. Then we have an electron Zeeman term here, which is exclusively along z, because b is only bz. This is fine structure term, which describes the interaction of the 2 electron spins. which is along Z anyway. This is protopole interaction, and also nuclear Zeeman interaction would be along Z in this case. And then the only term not commuted that is being able to drive nuclear spin dynamics would be hyperfine interaction. And as I told you in the beginning, this hyperfine interaction is dipolar in part. So there is one part of the interaction which is commutes with all the terms in the Hamiltonian, and then there is one part which does not. And it's this part, basically the hyperfine field orthogonal to the direction of B, which is determining the jumps of the driving around of the nuclear spin between its eigenlengths. And this is electron-nuclear spin interaction. Now you can calculate that basically the T1 time of the nuclear spin is a function of this orthogonal component, but because this hyperfine coupling is a constant value in there, right? You cannot do anything there, but it's also a function of magnetic field, and the dependence on the magnetic field goes as B squared. So if you plot the nuclear spin lifetime as a function of magnetic field, you see indeed that goes as B squared. And the moral of the story is that even for nuclei which do have a large orthogonal hyperfine component, for large enough fields, you will be able to see them in single shot readouts. So if you go back to our diamond crystal, this nitrogen-40 nuclei, you see the quantum jumps at a few thousands of Gauss. For carbon-13s, which are farther apart, which have a much smaller hyperfine coupling, you already see quantum jumps at this QND readout at smaller fields. That was about 200 Gauss, and you can take that one here. You see a slightly lower frequency, and you can see the quantum jumps even at smaller magnetic fields. So the gist of that story, the summary is that you, with every of these electron spins in the diamond lattice, you have a set of 3, 4, 5 nuclei, each of which you can see and read out in a non-demolition way. So all of these are small quantum registers. And I just give you now, well, a couple of results which came out the last couple of years, showing you what people did with that. So we did entanglement experiments between the electron and 2 nuclear spins. There is a very nice work by Misha and Peter Maurer showing actually that for these nuclei which have small couplings, T1 and T2 could be on the order of seconds, so that's beautiful quantum memory. Ronald Hansen, that's a paper which is probably it's already out in Nature Physics, shows Bell's inequality, so 2 particle correlations of entangled nuclei, and now there are upcoming studies doing quantum correlation from here to Z and these kind of things. Okay, so that's basically what I wanted to tell you. These are nice small quantum registers in actually a very easy to make system. And all of these experiments have been done at room temperature. And now, of course, I mean, the number of qubits you have accessible, the number of carbon-13 spins you have accessible there around an electron spin is limited, because addressing actually commences in frequency space, where there is limited frequency space. You want to scale up that system. That is, you want to combine individual nodes. And there are different actually methods being advocated and advertised and analyzed on how to do that. And I probably don't need to go through all of them, but apparently photon interference, that is having 2 defects emitting identical photons and erasing which path information by a beam splitter, is a very elegant way to entangle distant nodes. And there are 2 groups, Ronald and Misha, very actively working along that lines, and there are 2 nice papers which came out last year showing that indeed by beam splitter interference you can at least see hormonal interference of photon defects. People worked and analyzed the situation of 2 defects being in one cavity, sharing one cavity mode. There could be a photonic mode, there could be a mechanical mode also, right? So you can try to couple multiple defects to one mechanical oscillator, cool it to the ground state, having a very efficient quantum bus between those systems. All that is in the makings in different groups. And what we try to do is a very brute force and straightforward approach. That is, bring two spins so close together that they have two nodes so close together that they have strong magnetic dipole interaction.
Should we know why it's a cube root?
This one here?
Yes.
Oh yeah. It's basically so the it basically goes as a concentration. So T2 goes as a concentration, and this is where the cube root comes from, right? So that's so the maximum distance you can afford depends on T2, which depends on volume concentration. Right? Okay. So the our setting we try to realize as follows. So we have these, diamond defect center spin clusters, electron nucleus spin. Each of these clusters has an extension which is on the order of a few nanometers, maximum 3 nanometers. And we would like to use the electron spin as a strong magnetic moment to provide strong coupling between distant nodes. The typical length scale over which we have strong coupling is on the order of a few tenths of nanometers. And once again, that is determined by the dephasing of the electron spin in itself. And the dephasing depends on, for example, the presence of carbon-13 in the lattice. And since we have on the order of millisecond dephasing rates, you need to have kilohertz couplings, and that kilohertz coupling is on the order of, it gives you a distance on the order of 40 nanometers maximum. This is how this length scales. Okay, so keeping in mind that we want to have defects at distances of, say, maximum 40 nanometers, one needs to come up with nano preparation technology to, in a controlled way, position individual of those defects. And that's what we developed over the last years, starting from very basic implantation with an ion microbeam. So the way we make these defects, we implant nitrogen and then do annealing for the vacancy to diffuse to the nitrogen. That's how it goes. So we started, with lattices, with the lattice, with the spacing between nodes on the order of 10 micrometer, and now we play around with nano implantation techniques where we implant single nitrogen atoms through holes in atomic force microscope cantilevers. The size of these holes here is 10 nanometer, and that is roughly what determines the precision with which we can write now defects. And others, like they did shown on Andy's group, they use stationary masks with very small holes to have nano positioning of defects.
Should we think of these as just on the surface or close to the surface?
This is very close to the surface. So in contrast to phosphorescent silicon, where you have a kind of self-diffusion mechanism, right? When you position phosphorus onto a silicon surface, it diffuses below the first surface layer, right? That just if you look at the wetting energy, so to say, of phosphorus on silicon, then you come up with a situation that at room temperature phosphorus diffuses a few atomic layers into silicon. That's not the case with any impurity except hydrogen in diamond. Diamond is a lattice which you need at least 60 electron volts to kick out a carbon-13 and replace it by an impurity ion. So you always need this quite high kinetic energy to put something into diamond. And this is why, first of all, you need these kind of metal masks with a certain thickness to have, to make the ions go at specific locations. And this is why you need to always shoot them in with a certain kinetic energy. We typically use energies on the order of, say, 2 kilo electron volts, and then the nitrogen goes like 3-4 nanometers below the surface. That's how it is. And the positioning accuracy is mostly given by the size of those holes. It's on the order of 10 nanometers. Arrow bars are 5 nanometers, but could also be plus minus 10 nanometers. So that's, this is basically what's technically doable right now. But this is on the order of the distance, right, you need for a strong coupling. And so, this is how typically these spots look like. What we did here, we implanted individual or pairs of nitrogen with our through this AFM hole in the AFM cantilever. And then we look at each and every of these implantation spots and look, in this case, for two coupled pairs. And there is statistics in that process, and this is why we, on average, implanted 5 nitrogen lines here per spot. And then we take a super resolution optical microscope, which is this, probably you've heard about this STAT technique, which is, well, I call it a nonlinear optical microscopy technique with non-Gaussian beams. In any case, right, if you look into such a spot and you just do an optical fluorescence microscope image with this STAT technique, you see that you have all these dark spots here are individual defects, that you get, dimers and trimers with the critical distance. And this is how we prepare our samples. And I show you one example for the successful generation of a strongly coupled pair. And this is what you see here. First of all, this is, once again, an optical microscope image. Just look at the length scale here, right? It's 5 nanometers. And these are not simulated data, but these are real images. So one of the things you probably know is that you learn in school that optical microscopy is lambda half, so it's 500 or 300 nanometer resolution, but that's not true, right? Optical resolution, or at least the positioning and accuracy, or the accuracy by which we can determine the position of quantum systems is much better, and it's only limited by signal to noise. And this is so good here that we can determine the position of these defects with few nanometer precision. So these are roughly 20 nanometers separated, and these two defects, they are not parallelly, they are not oriented in parallel in the lattice. So these diamond defects, they are oriented, SNV centered along the 1-1-1 axis, and it just happens to be that these two defects we are looking at here are not oriented along the same 1-1-1 axis in the crystal. So if you now apply a magnetic field, and this is once again the spin-spin interaction, which is the interaction of the two electron spins within the system. If you add an electron-Zeeman term to that, then you get a term in the energy spectrum which depends on the relative orientation of the two defects. That is, if you now apply a magnetic field, the energy levels between these two defects, NDA and NDB, are shifted. And you can address these two defects in frequency space, and that's shown here. So this is nothing but, once again, the EPR spectrum, and these two lines here belong to the one defect, A being the two green arrows. These two lines belong to the second defect, B. And this is how we do local operations on the two defects. And we can convince ourselves that the two defects are strongly coupled, and this we do in the following way. So we look at one of the defects, say this one here, and then we selectively play around with the spin of the other defect, which we address in frequency space. Now, remember, these are spin triplets, and this is, and that means basically that you can switch off the dipolar interaction among the two defects. If we, for example, switch this defect here into M sub S0 sublevel, then there is no magnetic moment acting on NVA from this defect here. And then we do Ramsey experiments on this defect, and that gives us a kind of zero interaction frequency axis. And now we switch this defect here to say +1, and you see that the frequency response of NVA shifts in this case to low frequency side, and now we switch this one here to NV-1, you see it shifts to the other side. And this energy difference here is nothing but the dipolar interaction, which is on the order of 10 kilohertz, and it results in a distance of 15 nanometers. So that's all self-consistent, and you can convince yourself easily that here you have dimer, two defects, which are in the strong coupling limit. To the quantum dot experts here, because we have point-like defects, the two wave functions at a distance of 15 nanometers do not overlap. The spatial extension of the wave function of the electron spin is a nanometer. So we are at a distance which is roughly 20 times larger than the Bohr radius of the two defects. And this is why we have no tunneling, nothing. We don't even have resonant optical energy transfer between the two defects for reasons I'm not going to explain. So this is purely ground state magnetic dipolar interaction. And then you just go through your quantum toolbox of things to do. And one thing to do is, for example, prepare an entangled state like this one here, which we do with just Hadamard gates and in the phase gate. And this is a density matrix of two entangled triple electron spins, real and imaginary part. Imaginary part should be 0 or close to 0 as it is. And here you basically see that there are coherences between these two states, right? If you can read here the labels, you see that we have the coherences exactly where we need them. This is a bit larger than a classical 2x2 matrix because we have triplet spins here, right? So this is a 9x9 matrix. Makes experiments a bit time consuming. Fidelity, you can calculate from this is about 0.67, so it's just at the classical two quantum order, but it's safely in the quantum regime. Now, once you have done entanglement, you can ask yourself how robust is that entanglement? That's another critical question you need to ask yourself. So we looked at this should be entanglement here as a function of time after preparation of entanglement, and these are the decay curves. And you see decay times are pretty rapid, on the order of 20 microseconds, whereas T2 with these of these two electron spins is on the order of 200 microseconds or even a millisecond. So that's quite more rapid. And this is why we thought about ways to extend these entanglement lifetimes. And the way we did it is we swapped entanglement of the electron spins once again to nucleus spins, which we know to be more robust. And that's the quantum wire diagram. I guess I don't need to go through this, but I guess the effect itself is loud and clear. This is entanglement lifetime without nucleus spin storage, and this is entanglement lifetime with nucleus spin storage. So here now we are on the order of milliseconds, and that milliseconds is really the lifetime of the electron spin state itself. When the electron spin flips, it takes with it nucleus spin entanglement. So this is now where we are in our system, and the next steps we're taking is, so first of all, we have an entanglement of the nucleus spins here instead of the electron spins, although, of course, your interaction is very weak. So making that without the electron spin would almost be impossible. Okay, so this is now the next generation of systems we are working on. So now we have, over the last month or a year or so, we have improved our nano implantation technology, and we are now routinely writing these, say, 3x3 arrays. The distance here, look at the length bar, is 150 nanometers, so distance between nodes is just on the order of what you can afford with respect to T2. And we now try to generate multi-particle entanglement among these spins. I should add that not all of these spots here have single defects. That's a single defect, that's one. This one here, for example, you almost can see is R2 and so on and so forth. So there is certainly room for improvement, but I just wanted to give you a feeling that things there now really get more complex, and probably within the next couple of years or so we will really see larger arrays of strongly interacting spin systems. Okay, so yeah, with that I come to the last part of my talk, which now tries to make use of these structures, not in terms of making larger interacting spin arrays, but in terms of sensors. And that's an example of a recent image we have taken. So that's the second part of the talk. So what is the idea of that part of the work we are doing? Now, given that you have spins with very good coherence times, very good Q factor, so to say, of the magnetic dipole conditions, you of course start to think about using them as sensitive sensors. And they wrote a very beautiful paper on actually how to do very sensitive magnetic field detection with these defects. They are also good for sensing electric fields, simply because you have a very small spin-orbit coupling, and so the ground state spin splitting is also sensitive to electric fields. And actually you can sense electrons at a distance of, say, 200 nanometers. That's not, by the way, this is not an enormously good number. If you take a single electron transistor or so, It does it at distances of, say, 2 microns, so these are much more sensitive. But these diamond defects, they are point-like sensors, right? Their size is angstroms, and so you can hope to really, contribute, for example, to microelectronics, as you see here. Same is true for magnetic field sensing, and they are also very good sensors in terms of optical interaction. So if you want to probe local optical fields in the near field, these defects are also very good. But right now, for the rest of the talk, I will mostly concentrate on that part here, because that's where we have made most progress. And what we want to do is here, actually, we would like to use that for applications in life science. So that's actually the goal we have set ourselves, trying to see single electron spins on, for example, the DNA here, which is an acid, as you know, so there are lots of unpaired electron spins, so that's a paramagnetic structure. So this is one of the things we would like to do. And now let's see where we are there. Now, actually, we got inspiration from how we do that from medicine. Probably once in a while, I'm sure you read Science or Nature, and once in a while you will have come across such images here. And what these images actually are is, or they are called BOLD, blood oxygen level dependent functional MRI. MRI stands for magnetic resonance imaging. And what these images actually are is they measure a relaxation map of protons, in this case, inside the brain. So magnetic resonance imaging measures the density of protons, the density of water, basically, in your body, right? So here, this is the skull bone. There is little water in there, but this is the brain, substance cells. So there is lots of water in there. That makes a contrast in these images. Now, in addition to just measuring the density of water, of protons inside the specimen, what this functional MRI does, it measures the relaxation time, T1, longitudinal relaxation or lifetime of Nucleus Banks in a specific state. And this is obviously different here in the brain, and it's particularly large in these areas where you find red and blue. And the way this relaxation time is linked to function is very simple, right? Oxygen is, as you know, a ground state paramagnetic molecule, right? Oxygen, O2, is a ground state paramagnetic species. And the electron spins, paramagnetic electron spins of oxygen cause relaxation of nuclei. So their noise spectral density has a frequency component at the lambda frequency of the nuclei. So whenever there is lots of blood with lots of oxygen, nuclear spin relaxation is very fast. And that's what you see here. The parts of your brain which are active use lots of oxygen, or there is lots of oxygen passed by, which is, and this makes proton relax fast. And these two parts here, this is the front part of the brain, and this is the rear part of the brain. And this patient here was obviously listening, because these are here. This is the audio cortex of your brain, and this is the visual cortex of your brain. So this patient here was listening and looking to something, right? And this is why these parts light up. And this is exactly the method we use for doing magnetometry, sensitive magnetometry on biological specimens. And we do that in two ways. One is we just convert a regular optical microscope, which is it's a plain and very simple fluorescent microscope, into a imaging magnetometer. And the way we do it is we put our sample on top of a diamond, and what we image is the fluorescence intensity of the diamond defects, and we image that onto the CCD. Now, with that is we position our diamond defects very close to the surface, and then in a kind of test experiments, we put paramagnetic molecules, no oxygen, but oxygen also works very nicely, into a liquid on top of the sensing layer. Now these spins here, they move inside the liquid, right? And this causes the magnetic moment to tumble around. And if you look at the magnetic field being caused by this specimen here, as a function of time, you just see noise. There is a large noise spectral density for this specific specimen. That's, by the way, gadolinium which has 4 unpaired 4f electrons, so it has a large magnetic moment. So basically that causes noise, and this nitrogen vacancy layer is nothing but an antenna for that noise. And since we image this nitrogen vacancy layer onto a CCD chip, we basically get an image of the noise on top of the specimen. Of course, we adjust what we just actually measuring here is the noise. So the average of the field is 0, but the standard deviation is not. And it's this deviation from the standard deviation from 0 which creates our noise. And one thing is, for example, we made a polymer layer on top of the sensor, which at certain parts contained gadolinium and in others not. And then we just measure the T1 map of the nitrogen vacancies beneath, and you see where there is no gadolinium, you have long T1, where there is gadolinium, you have shorter T1. We also made a more bio-like system by having a microfluidic device on top of a diamond layer. Now the unpaired spins, electron spins, are in the fluid, they are tumbling, causing noise, and so that's a flow cell arrangement, and then we just measured the relaxation time of the NVs as a function of the concentration of spin specimens in here, and we step by step, this is a graph here where we look at the fluorescence intensity of the NV as a function of gadolinium spin concentration, and you see as so the fidelity, the contrast of the signal goes down, and here that's our sensitivity limit, and that is basically 100 gadolinium spins per voxel we can see there. By the way, there are no microwaves associated or involved in this system. It is just the magnetic field noise component of the spins at the Lama frequency of the nitrogen vacancies which contribute to the signal, right? So you basically really use the NV centers as an antenna at their Lama frequency for magnetic field noise. Okay, so we also did try to do cellular images with that, and this is now a HeLa cell, which is a cancer cell, here in bright field, and this is in fluorescence image, so we stained it with fluorescent dyes, and this is the T1 map, and this cell causes spin relaxation of the diamond defects because we have doped it with spins, with gadolinium. And we improved that image recently by just staining the cell membrane with gadolinium with paramagnetic spins, and you can see a value that you can see, I guess, just the cell membrane in the T1 map. So these are the first bio images with these with subcellular resolution with these kind of magnetometer. If you want to go better, if you want to do it better, you simply need to go into the near field of the spins you're probing. So this is basically a wide field experiment. It's very simple. It basically just takes a normal fluorescent microscope and this diamond converter chip. If you want to do that better, you need to go into the near field. And going into the near field means that you really, you need to do it in a scanning probe device. And that's something, that's the last thing I'm going to show you, which we did a while ago. So what we do is we take an ordinary atomic force microscope and put a diamond spin, an NV spin, at the very end of that tip. Mostly we do this with nanocrystals, which we glue to the end of the tip. Other people, like in Ami Jacobi's group, for example, Patrick Maletinsky, they develop very nice diamond tips. Now, what we did with this, we measured the magnetic field noise of single proteins, and this is a very, very particular protein we used here in the beginning. It's called ferritin. Ferritin is a spherical protein. It has a dimension, a distance, a diameter of 10 nanometer, and it's full of iron. So it can have a couple of thousands of iron atoms. And actually, this protein is also existent in our body, and what it does, it actually stores iron when we don't need it. So if you don't do sports, right, and you don't do any hiking or so on and so forth, usually you have an excess of iron in your body, and instead of expelling, the body stores it. I mean, iron binds oxygen, right? So it's actually the chemical species which makes your blood red. And if you don't need that many oxygen-binding iron in your body, then it's stored in this ferritin. And from there, it's retrieved when you start to do exercises. And so this is an AFM image of this ferritin. On top of the glass cover slip, you see these tiny dots here, which is just topography. And now what we do is we scan our sensor across the surface, and when we put our sensor on top of the bare cover slip surface, you see this is the relaxation curve of the NV inside the nano diamond. And if you put it on top of ferritin, you see it's drastically shorter. And once again, what happens here is you see the fluctuation of the iron, and you are sensitive to the fluctuation at the long frequency. And this is now a relaxation image of that protein, and you see here this dot, and look at the length scale, right? This is on the order of 20 nanometers, and that's even slightly better than the topography or the topographic resolution of our AFM. Okay, and we try to do that even a bit better, and that's now the last thing you are going to see. We try to measure single proteins inside a Tabak mosaic virus. So these Tabak mosaic viruses are very nice species and entities, biostructures. When you start to do biophysics when as a physicist you start to do biology, I should put it that way, because you can very easily control them. You can put them in UHV and under low temperature, and they remain, or they keep their integrity. The way that these viruses are produced is actually that these protein slices, these are donuts, protein donuts, which line up along the RNA of the virus. And you can, for example, fasten that RNA on the cover slip, and then you can have these viruses growing on top of that cover slip. That's at least what biologists in our department can do. And now this is once again an AFM image of such a viruses lying flat on top of the substrate. Length is on the order of 300 nanometer, diameter is on the order of, 30 nanometers or so. To make them visible for the magnetometer, what we did is we coated that protein by genetic modification of the protein with electron spins, once again with this gadolinium compound. And this was one of our first images of a Tabak mosaic virus, just by measuring the quantum relaxation of a single defect inside this AFM tip. And here you see the contrast, which is not very good. But what we did then is we improved the method, and most notably what we did is we were growing the Tabak mosaic virus with normal proteins. Then we were exchanging these normal proteins by genetically modified proteins, which only bind, and which were the only proteins to bind these spins. Then we were exchanging the culture medium once again, regrow with normal proteins, and so on and so forth. So this is a kind of, like an MBE machine. You do that, but instead you do it with these viruses. And these are now our most recent magnetometry images. So here you see the virus once again. And whenever you have this slice of spin-modified code proteins, you see that the T1, and this is the scale here, is reduced. And the resolution here is on the order of 50 nanometers. That's about 2 layers of two stacks of these proteins here, these protein slices on top of each other. And the sensitivity we have is on the order of 50 electron spins. Now, these 50 electron spins are not polarized here, right? They are fluctuating. You look at their fluctuations. So the effective magnetic moment is the square root of that. So that's on the order of 7 times the magnetic moment of a single electron spin we can see here. And that's done at room temperature in a laboratory environment, water and dust and whatever you have around here. Okay. So that's it. So basically the summary of the talk is I wanted just to give you an idea that these diamond defects is more than just the electron spin. It's always a small cluster of carbon-13 spins around, which you can read out, for example, with high fidelity, with single shot readout, and do entanglement, and probe quantum correlations, and so on and so forth. The field, and we are not the only one to work there, is now in such a state that we start to couple deliberately placed nodes, that is, spins, with each other, and try to do that in such a way, our experiment in such a way, that we nevertheless have single-side readout. And I guess magnetometry is now actually is on its way to bio, where I see one of the applications, and we are now at a level where we can see 50 to 100 electron spins, thermalized electron spins, that is non-polarized electron spins. You probably have seen when you look at the archive or have listened to one of the talks of Ali Jacobi that he and his group now succeeded in seeing single electron spins inside diamond. So they are emitting spins inside diamond, which have much longer relaxation times than all of the spins you find in nature. Okay, so this is the group showing you two things. First of all, that there are mountains in Germany. Well, actually, these are mountains in Austria. That's almost Germany. We are living in Europe anyway. Right? And this is part of the group which made it to an altitude of 1,500 meters. I particularly would like to thank Fedor, who is here in the back, who is since 1 year or so a professor in Ulm, running his own group there. And this is Gopi, who was actually in charge of all the magnetometry experiments in the beginning, and who is now heading a junior research group at the Max Planck Institute for Biophysical Chemistry in Göttingen. And Friedemann Reinhardt is now running all the magnetometry experiments in Stuttgart. We have collaborations with people all over the world, a couple of US groups, most notably the Harvard guys, Australia, France, and so on and so forth. We get money from different sources, also a bit of money from the US, which I'm particularly proud of. Okay, so I thank all those people, and I thank you for your attention. Thank you.